Well, hello! Look who's here today. I'm glad you came to class. I don't know how to start these videos. This is dumb. All right, so we're going to do some Pivnert problems out of the week 31 packet. Hopefully you've already tried to work a good number of these. I'm only going to work a couple of them, but if you're struggling with them, right, come to the Google Meets. We started having more people do that and getting some help there when they need it, so that works. So we'll do number 5. Right, so this is number 5 on the Gaslaw Pivnert worksheet with the whale on it. If you haven't done that one, not a bad idea to pause me on here and try and work that one. Or if you're really struggling, maybe go ahead and have me work for a little bit and then pause and see if you can work ahead a little bit. And those kinds of things will help you work your way through that, right? So I read the question. It says, an unknown gas takes up 400 liters of space when the temperature is 35 degrees Celsius in the presence of 690 millimeters mercury. How many moles of gas are present? They're not talking about changes. When they talk about pressure changing and temperature changing and volume change, those Boyle's law, combined gas law, Charles law, Gay-Lussac's, all that kind of stuff. When you just hear them talking about one sample of gas and they're just a bunch of information about that sample, it's probably a Pivnert problem, right? So as we go through, the pressure they gave us was 690 millimeters of mercury. The volume they gave us was 400, right? 400 liters with a decimal point. So I get to keep all 3 sig figs. I've got what looks like 2 sig figs here, right? 3 sig figs here. Don't really need to worry about those until the end. They're asking for a number of moles. R is, of course, 0.08206 liters atmospheres per mole Kelvin. And the temperature they give us is 35 degrees Celsius. So I'm going to Dora the Explorer you here, because I remember when my kids were little and we'd watch Dora and she would ask a question and then just stare at you. So what do we need to do before we start solving this problem? Did you answer so that we weren't just sitting there awkwardly staring at each other? So I don't know if you answered because I can't hear you. But hopefully you said you got to change your units because your units aren't going to work because you've got Kelvin here and Celsius here. So we got to add 273. Right, so I add 273, and that's going to give us, 308 Kelvin. And there's one more unit that I've got to change. Which one? Yep, it's millimeters of mercury. You got it that time. You got it. The first time was shady, but that second time we figured it out. So 760 millimeters of mercury for every 1 atmosphere. Where do we get these numbers? You're probably, hopefully you're not thinking that, but maybe you're thinking, where do we get these numbers? How do I know what relationship that is? That's on the back of your periodic chart. Remember, on those things that are equal, there's all those pressure conversions that we've got there. So I've got to multiply 690 by 1. 690 times 1 divided by 760 will give us 0.907 atmospheres. Right, so I've got atmospheres, I've got liters, I've got number of moles, I've got R, and I've got Kelvin. So all my units are going to work. I want to do that before I start solving the problem. Then I can just plug it in and solve the problem. So the equation is PV equals nRT. I prefer to rearrange variables because I'm lazy and I don't like to rewrite stuff a bunch of times. So if I was doing this, I'd just divide both sides by RT and do it that way. But most students prefer to write the problems out. So that's going to take a little bit more space. So 0.907 atmospheres, that's my pressure, times my volume is, not a V, times my 400 liters equals that number of moles that we want times 0.08206 liters atmospheres per mole Kelvin. And then lastly, our temperature, 308 Kelvin. Hopefully I'm still on the screen. Hey, look at that, I'm still on the screen. It says 308 Kelvin there if you're having a hard time seeing that. So since n's but the thing I want, I need to get rid of these things. So they're attached by multiplication. So I'm going to divide to get the n by itself. So we divide both sides by 0.08206 liters atmospheres per mole Kelvin. And we divide by 308 Kelvin. So over here, both of these cancel out. And here I'm doing PV divided by RT. So if I had done it by variables, I would just divide both sides by RT to get the n by itself, right? So however you like to do that, just make sure we're able to do that in some way. So 0.907 times 400 divide by 0.08206 divide by 308 Be careful, don't hit divide by times unless you're putting parentheses because it'll pull that 308 on top. So you should be running calculations there with us as we do that. And that gives us 14.35 moles equals N. We don't have that many significant figures. Realistically, we've got 3 here because that's addition to the ones place. We've got 4 here. We've got 3 here and 2 here. So really I should round my answer to 2 sig figs. So that would be 14 moles would be my best answer there. I don't want us freaking out so much about sig figs that we lose the point of things, but we should keep track of good sig figs. So 14 moles is your answer for number 5 there. So very exciting demo we're going to do now. Actually, I do really like this one. The match part's not all that exciting. But now, before I do my demo, Dora the Explorer time, what am I doing wrong? Oh, no goggles. Got to wear goggles. Got to goggle up for science. So I'm going to goggle up for science here. I've got my candle burning. I have a couple 2 liters of empty 2 liters, and we put this in here. Look at that. Isn't that amazing? I know. That's amazing, right? So cool. That's the end of the demo. No, that's not the end of the demo. So what we're going to do now is we're going to put something in our 2 liters. We're going to go ahead and put some baking soda. Oh, that's where my scupula was. I was looking for that scupula. Apparently, sloppy chemistry teacher left a scupula in the baking soda. So baking soda, sodium hydrogen carbonate, right? If I put sodium hydrogen carbonate in with some acid, right, we make carbonic acid. Carbonic acid decomposes to carbon dioxide right away. So we make carbon dioxide in there. So now, remember before we were like this, and now, look at that. How come, right? HC, how come? What does fire need to burn? Fire needs oxygen. In here we generated CO2, so if we generated CO2, that CO2 is keeping oxygen from getting to the flame, so it puts it out. So now comes my favorite part of the demo. What's happening right now? I can't see anything. This is weird. I think Mr. Fred's going crazy during quarantine. He needs more human contact. Do you have an idea? Do you know what I just did? Remember, that was the one that put it out before. Right? I poured the CO2 from one container to another. So CO2 is a gas. Gases are fluids. Fluids you can pour. And if one is more dense than the other, you can displace it. So it's messy and sloppy. That's why I had to go really slow there. I haven't actually lost my mind completely, right? So, but CO2 is more dense than air, so it's able to push the air out of the way, right? Gas density is kind of a big deal, right? So let's work a couple problems. But we can do quite a bit with gas density, actually. So we can predict what things are going to float and sink. We can know how heavy air is. We can figure out the buoyant force of air and figure out how many balloons it would take for you to fly up into the air. It's about 5,000 for what it's worth. But we can do that calculation sometime. So anyway, if we look at number 9, right? So go to number 9, and that says, what is the density of a gas if it has a mass of 15 grams and a volume of 35 liters, right? So that's not one of our Boyle's law, Charles law kinds of things. That's just an old physical science density question, right? And we remember from physical science, what's the equation for density? I'm sorry, I can't hear you. What's that now? That's right. Density is love. Density is love. Density is love. And it's like a heart. Oh, remember you put a line through it because density is mass over volume. Oh, density's love. It's so sweet, right? We're past Valentine's Day, so nobody cares anymore. So all I have to do is take the mass, which is 15 grams, divided by the volume, which is 35 liters, and we do 15 divided by 35, which I don't feel like doing in my head, and that is 0.428 grams per liter, right? So the densities of gases are not very much, right? You can imagine the mass of a gas is not going to be a whole lot. So let's go ahead and do a generic density problem for CO2, right? So we'll compare CO2's density to nitrogen's. Sorry, this video is getting a little bit long, but we'll do that at room temperature and pressure. I'll try and work through this pretty quick. But if I want to know the density, it doesn't matter how much I have. So I'm going to pick an amount that is easy to work with. So I'm going to pick 1 mole. Right? I'm going to pick 1 mole because that's going to make both of my problems easy. Because if my gas is CO2 and I pick 1 mole of that gas, and it's CO2, I just need the molar mass of the gas to get the mass part for my density equation, right? So if I have 1 mole as my amount, then 44.01 grams is the mass because that's the molar mass of CO2, right? 1 carbon, 2 oxygens, 12.01 plus 32 kind of thing, right? In the room, so that's 1 atmosphere of pressure. I'm looking for the volume. R is 0.08206 liters atmospheres per mole Kelvin, and the temperature is 298 Kelvin. We typically say room temperature is 25 degrees Celsius. So going through kind of quick because the video is getting long. So volume is going to equal nRT over P. So that's going to be 1. I'm going to skip units to save some time. 206 times 298 Kelvin divided by 1 atmosphere. And that gives us a volume of 24.4 liters. Just a little bit more than the 22.4 we got at standard temperature and pressure, right? Because standard temperature would be 273 and standard pressure would be 1 atmosphere. So almost the same as that 22.4 conversion factor we had from earlier this year. So we do 24.4 liters, and the density of CO2, 44.01 divided by 24.4, the density of CO2 is 1.82 grams per liter. And that must be more than nitrogen because we just saw it displace the nitrogen. Well, we didn't see it displace the nitrogen. We saw the effects of it. So this would be for CO2. For nitrogen, notice nothing about the chemical is in here. So 1 mole of nitrogen would take up the exact same amount of space. So for the nitrogen problem, we would still do 24.4 liters. Oxygen's about the same because it's about the same molar mass. So if I was doing nitrogen or oxygen, I could then put that molar mass on top, and nitrogen's 28.02. So 28.02 divided by 24.4 is going to give us 1.14 grams per liter. Or if I was doing oxygen, 32 divided by 24.4, it's 1.3. Yeah, so 1.14 versus 1.3. So those are pretty close, so they can mix. But we see our CO2 is more than our nitrogen. So our CO2 is heavier, it's going to sink. Our nitrogen is lighter, so it's going to float. The main thing, or the easiest thing about the sink and float thing is all that really matters is the molar mass, right? My volumes are the same. So if I have a higher molar mass, it's going to sink. If I have a lower molar mass, it's going to float. We'll play with that a little more down the road a little bit, but want to at least introduce gas densities to us and that kind of stuff. So hopefully that helps. Keep working through those packet problems and stuff, and let us know if you're having problems.